Welcome back to The Explainer. Today, we are unpacking something absolutely huge. We're diving into advanced agentic patterns in LangGraph, specifically using the functional API. You know, when we all first start building AI applications, we usually stick to a basic linear workflow, right? You ask the AI to do a task, it does it, and it gives it back. Super simple. But if you've ever actually tried to scale that up, you quickly realize that those basic linear AI workflows, they simply cannot handle complex, diverse tasks efficiently. Well, today, we are going to fix exactly that. Okay, let's map out our scaling journey for today. First up, we'll tackle the concept of AI routing. Second, we're going to look at network errors and the try policy. Third, we'll cover parallelization to save you time. And finally, we'll wrap the whole thing up with tasks and stateless execution. All right, let's jump straight into part one, the concept of AI routing. So, if you're expecting one single LLM prompt to perfectly execute every single possible user request, honestly, that is just a recipe for disaster. We absolutely need a decision maker. To wrap our heads around this, there's this brilliant analogy from our source material, the university guard. Imagine walking onto a massive, sprawling university campus. You don't just wander around aimlessly hoping to stumble into the right class. You go to the main gate, you talk to the security guard, and you tell them what you need. Looking to enroll? The guard sends you to the admissions office. Need to study? They send you to the library. The router pattern in LangGraph works exactly the same way. It's a system where an initial decision maker evaluates your incoming query and routes it directly to a specialized agent or department. Let's walk through how this actually flows in the code, step by step. Step 1, your system's entry point receives an input query, which is typically formatted as a data dictionary. Then, step 2, the router takes over. Now, this router can be a randomized function if you're just testing things out, or in a real-world scenario, a dedicated LLM whose only job is to analyze and categorize that query. Step 3, based on that analysis, the router conditionally triggers the right handler function. It sends it to the math department, the writing department, or maybe a general catch-all department. And finally, in step 4, that specialized department processes the query and fires back a highly accurate response. Why is this such an absolute game changer for developers? Well, think about it. Technical documentation requires a totally different logical approach than writing a creative podcast script. You really shouldn't ask a technical writing agent to be funny, unless, you want your API documentation to read like a Shakespearean tragedy. Routing prevents you from blocking the LLM on a single massive confusing prompt. It also gives you a dynamic fallback. If the router gets a completely bizarre random query, it safely directs it to a general category instead of crashing the whole app. And the best part, no matter which department actually does the heavy lifting, the output is captured and stored in a single unified response variable for the user. Moving right along to section 2, network errors and the try policy. Okay, so our code is beautifully routed, it's smart, but what happens when it smacks into the messy reality of the internet? Because here's the thing, perfect code on your local machine means absolutely nothing if it can't survive production. When you test locally, it's a controlled environment. Everything works. But the second you push to production and suddenly get a spike of 1 million users, you're gonna hit network latency, API rate limits, all sorts of chaos. If your application crashes just because an external API took 1 extra second to respond, your users are gone. We have to design for failure. This is exactly where LangGraph's try policy swoops in to save the day. It's highly configurable and lets us gracefully handle those inevitable network hiccups. Let's break these settings down. First up is the interval. This is your starting delay, like waiting half a second before trying again after a failure. Next is the backoff. This is a multiplier that gets applied to your delay after every single failed attempt. Then we have the max interval, which is your hard ceiling. It's the absolute maximum time the system is allowed to wait between retries, just so it doesn't hang there forever. And finally, max attempts. This ensures that if the network is truly hopelessly down, the system will eventually stop trying and properly report an error. And this perfectly illustrates exponential backoff in action. It is such a genius healing mechanism. Let's say your first call fails. The system waits 0.5 seconds and tries again. Still failing? It applies that backoff multiplier. Let's say it doubles the wait time to a full 1 second. Fails again? It waits 2 seconds, then 4 seconds. And if we set our max interval ceiling at 8 seconds, it hits that limit and stops growing the wait time. It gives the stressed out network the breathing room it needs to recover without hammering the API with aggressive back-to-back retry requests. All right, section 3, parallelization and saving time. So our system is smart and it's resilient. Now, how do we make it fast? The secret here is parallelization. Comparing these two approaches always gives developers a massive aha moment. If you stick to standard linear prompt chaining, you wait for task A to finish, say that takes 30 seconds. Then task B takes 10 seconds. Then task C takes 10 seconds. You just made your user wait 50 total seconds. But if those tasks don't actually depend on each other, we can use parallelization. We fire off task A, task B, and task C all at the exact same time concurrently. What happens? Your total wait time plummets from 50 seconds down to just 30 seconds. To really ground this concept, let's use a great real-world analogy from our sources: bank onboarding. Picture a new customer walking into a bank to open an account. The bank manager doesn't just run one background check, sit around waiting for it to finish, and then start the next one, right? No, they assign 3 workers simultaneously. Worker 1 checks for a criminal record. Worker 2 verifies the national ID. Worker 3 checks for external bank defaults. All 3 workers are executing their jobs at the exact same time. Once all 3 report back, the manager aggregates all that data and makes the final decision on the account. The absolute beauty of this setup is that your total wait time is literally only ever as long as your single longest task. By leveraging your hardware's CPU cores and threads to run these processes concurrently, you are maximizing efficiency and massively improving the user experience. You're handing them an answer in 30 seconds instead of making them stare at a loading screen for almost a minute. So let's look at the actual code-level implementation in LangGraph. Step 1 is collecting all the tasks you want to run into a Python list. Now, because we haven't actually asked for the results yet, these are stored as future objects, which is essentially just the system's promise that a result will exist very soon. Step 2, you request their execution concurrently through the system's entry point. In step 3, we use a command, typically .result, to resolve all of those future objects simultaneously. The code just pauses, waits for every single concurrent task to finish its job, and then, in step 4, it gathers them all up and returns one nice aggregated response. And finally, Section 4, Tasks and Stateless Execution. We've covered routing, resilience, and speed, but what is the actual engine making all this possible? It's the @task decorator. It is so elegantly simple. You literally just place this decorator right above your standard Python function, and LangGraph wraps it in magic. It instantly transforms a totally normal function into an asynchronous node. And not only does it run concurrently, but it also becomes state managed within your workflow. That means the system tracks its exact progress. You really see the immense value of this when you compare it to a standard Python function. Think about it. If a normal Python script runs for 10 minutes and then fails on the very last step, boom, you lose all that context. You have to restart entirely from the beginning. But with a LangGraph task, state is persisted. If your workflow needs to pause to ask a human for approval, or if it temporarily fails because of a network error, it does not forget the past. When it wakes back up, it resumes exactly where it left off. You don't lose any of your prior expensive computational work. But here is the wild paradox that makes this specific architectural pattern so unbelievably powerful. Even though LangGraph tracks their progress in the workflow, the tasks themselves are fundamentally stateless. What does that mean? Well, unlike older stateful graphs that required this massive, rigid, global state, these functional API tasks are totally independent execution units. They just take in dynamic inputs, like a dictionary, do their specific job, and return an output. They do not care about the global environment at all. So let's wrap this up with a bit of a thought experiment for the future. Because these tasks are stateless, meaning they function almost exactly like Lambda functions in cloud computing, they can be executed absolutely anywhere. So think about this. What is stopping you from orchestrating an AI workflow where your entry point is sitting in a US data center, your heavy math task runs on specialized hardware in Saudi Arabia, and your creative writing task executes in Pakistan, all communicating flawlessly? The answer? Absolutely nothing. The scalability here is practically boundless. I really hope this explainer has sparked some amazing ideas for your next AI build. Thanks so much for joining me, and keep building.